All right, coming to you live from CVPR EarthVision. My name is Jake Shermeyer, and I was the challenge manager for SpaceNet 6. Today, we're going to be presenting the SpaceNet 6 challenge overview. Also joining me today is the SpaceNet general manager, Ryan Lewis, the SpaceNet 3, 5, and 7 challenge manager, Adam Van Etten, our baseline lead for SpaceNet 6, Daniel Hogan, from Capella Space, Jason Brown, and from Maxar Technologies, Todd Bacastow. So without further ado, I will turn it over to Ryan to give our SpaceNet overview.
Thank you, Jake, and thank you everyone for tuning in to our presentation today. Before we get into the specifics of the SpaceNet 6 challenge, including both an overview of the data set, algorithmic baseline, and then most importantly, the results, we'd like to give you a brief background into our SpaceNet organization, some of the work we've done previously, and a little bit of insight into what we see coming down the pike. Next slide. SpaceNet is a nonprofit organization that is focused on accelerating open source geospatial analytics. And it does so in concert with these 9 partners. Next slide, please. SpaceNet consists of 4 key pillars. First, we develop and publish labeled datasets. These datasets are associated with a specific challenge. Second is that we host public data science challenges. Third is that we open source the results from those challenges. And last but not least is that we publish detailed evaluation of both the models that are derived from the challenges, as well as the data sets. To date, on the data sets, we have 11 geographic areas. These are focused specifically over cities. To date, we've also hosted now 6 challenges, which total $300,000 in prize money. We have open sourced 23 algorithms, and in the next couple of weeks, we'll be adding 5 more, which are coming from the SpaceNet 6 challenge. And you can find our detailed evaluation in both papers and blog post series, which we will be providing links to later. Next slide. One of the key things that we've learned in the SpaceNet community over the last 4 years is that there are several key characteristics in terms of enabling open source innovation with both the data sets and some of the code that are derived from the challenges. And a couple of key things to remember here is that first, we focus specifically on enabling availability of the data set. So with each data set that we produce, it is licensed under a Creative Commons 4.0 share-alike license, which allows both commercial organizations, academics, and nonprofits to leverage the data sets for their specific projects. Also, focusing on accessibility, the data sets extend beyond a specific challenge. And so you can find data sets dating all the way back to our first challenge, SpaceNet 1, which was launched in 2016, on our Amazon Web Services S3 bucket, which is hosted under the Amazon Open Data Program. And last but not least is we've been increasingly focused in the last year on enabling interoperability of our data sets. So this includes enabling our data to be both cloud optimized GeoTIFF or COG, as well as spatial temporal asset catalog compliant. Next slide, please. Our data set consists of 2 parts. First, the raw imagery, and then second, the labels. First, on the imagery. As I mentioned, we have 11 geographic domains currently in our data repository. A majority of our data sets are electro-optical, provided by Maxar's WorldView 2 and WorldView 3 satellites. Over the courses of our challenges, we've added increasingly diverse data sets of different geographic domains, as well as seasonality. As Jake and the team will highlight later on, the SpaceNet 6 was also our first look into a multimodal challenge. So including both electro-optical data as well as high-resolution synthetic aperture radar provided by Capella Space. Next slide, please. The SpaceNet mission is focused primarily on foundational mapping. As a result, our two label features are building footprints and road networks and labels. To date, we have a little under 1 million building footprint labels across the geographic domains I mentioned, and we have a little over 20,000 kilometers of labeled road networks. Next slide, please. With that, I'd like to turn it over to Adam Van Etten, who will talk through our challenges to date and our strategy behind how we structured each technical challenge. Adam, over to you.
Thanks, Ryan. Right, so we've had a number of challenges clearly, and if we go back to the start with the first SpaceNet, we were trying to figure out how to get started with this foundational mapping mission, and we ended up picking building footprints, which is something that some people think actually a pretty easy problem. I actually thought that as well. Turns out it's still very much far from a solved problem, and so we started with building footprints in one city. So SpaceNet 1 was just Rio de Janeiro. And then we steadily kind of ramp up the complexity. So instead of just going for a moonshot, we're just iterating, building up complexity, and then allowing the kind of competitors and the whole ecosystem to catch up with really what's available in the open source and what can be done with these very challenging tasks. So SpaceNet 2 was building footprint, but with 4 different cities. So looking at geographic diversity. SpaceNet 3, we pivoted to roads. So this is maybe the second feature you'd really care about with foundational mapping, is looking at roads. So we had 4 different cities there. We're looking at not just the road pixels, but the actual network that we're trying to extract something that's a lot more useful than just pulling out an image. SpaceNet 4 was another really interesting tweak, which was looking at building footprints again, but this time off nadir. So this very unique collect over Atlanta, we had 27 different shots at different angles as the satellite passed overhead. So anything from 54 degrees off nadir to 7 degrees off nadir. And this allows us to look at how well algorithms can pull out buildings, even if looking at a very, very odd angle. SpaceNet 5, we were looking back at roads, but this time looking at not just the network, but also travel time estimates. So something you actually might care about for doing optimized routing. And then, of course, SpaceNet 6 was the first multimodal challenge where we looked at both electro-optical and SAR. So you can kind of see as we go forward in time, it's building up the complexity of the challenges. Next slide. So we've had increased user growth, which is very exciting. Over 500 million total repository hits and many, many terabytes of downloads. Again, we have these 23 open source algorithms with more coming very soon, and a very significant ramp up in challenge submissions. So we saw a huge increase in submissions for SpaceNet 6, which is always what you want to see, and participation in 82 countries at this point. Next slide. So I'll hand it back to Jake now for SpaceNet 6.
All right, thank you, Adam. Yeah, so the SpaceNet 6 challenge, we called it the multi-sensor all-weather mapping challenge. And this is, of course, a tip of the hat to our 2 components here. So SAR and electro-optical data. As Ryan and Adam talked through, this was situated over Rotterdam, the Netherlands. We had about 120 square kilometers of data here. So we had a near simultaneous collection of SAR and electro-optical. And really the multi-sensor all-weather mapping, all-weather component of this really goes and is pointed towards the SAR data. SAR sensors are unique as they can both penetrate clouds and operate in any illumination setting. So as such, they're particularly attractive in a disaster response scenario. If you can envision a hurricane blowing in, oftentimes you're going to have severe cloud cover, and that's going to render your electro-optical sensors inusable. So SAR really is complementary, and the ability to penetrate clouds is certainly attractive. Be able to generate a map of the surface quickly and effectively. So as such, the purpose of our challenge really was to investigate how well SAR data could do the task of building footprint extraction, increasing that complexity from our past SpaceNet challenges, We have good baselines already that exist for optical data and for extracting building footprints. However, for SAR data, really those baselines don't exist. And furthermore, there's really a lack of open, high quality SAR data available. This data set was really one of the first of its kind to feature very high resolution SAR data, and I believe the largest extent of this collection. So something we're hoping to continue to grow and incentivize research and development in the SAR domain. So that's really our primary motivation, baselining the performance of AI algorithms and computer vision techniques to detect buildings in SAR imagery. And our second goal here was to test if optical data can be used to augment or improve SAR imagery in any way. And we structure the challenge such that in our training data set, we had both optical and SAR data. However, in the test set, we only have SAR data, and only SAR can actually be used to map our buildings in this case. However, the optical data could be used to pre-process the SAR in some way or pre-train algorithms. The SpaceNet 6 timeline, we released the data set on February 10th. It's available in our S3 bucket through the AWS Open Data Program. All of our data sets are there, so you can go and download them today, and we encourage you to investigate that. We released our algorithmic baseline on the beginning of March, on March 4th, and the challenge actually launched on March 16th, running for about 6 weeks until May 1st. Throughout that time, we had over 1,600 solutions and over 400 registrants. So a very successful challenge. We saw a lot of people getting competitive, trying to win this challenge. We offer some aggressive cash prizes here, over $50,000 plus our $15,000 in AWS Compute. 45,000 of that is split across our top 5, with the remaining 5,000 going to our top graduate and undergraduate winners. And the AWS Compute is particularly important as it can enable people who don't have GPUs to actually participate in the challenge and start to work with the data and learn how to build some deep learning models at zero cost. And finally, here we are today at CVPR EarthVision, where we'll be talking more and more about the challenge and the results of it. So just to continue to discuss the data set in a little bit more depth. So this is really the components of the SpaceNet 6 data set. And joining me today are Todd Bacastow from Maxar and Jason Brown from Capella. So they're going to be walking us through some of the unique components of this. But as a general overview, we have SAR and electro-optical data. In the image on the left here, we can see the relative look angles of the SAR data. It was an aerial collect captured from about 35 degrees off angle, captured from north and south facing looks. And also we have a single Maxar worldview 2 scene. So the front, this GIF on the right, we can see the image strips being captured in time, and we can see the optical scene in the background. And with that, I will turn it over to Jason to give an overview of the SAR data and some of the elementary aspects of SAR.
Thanks, Jake. I'm Jason Brown. I'm responsible for the community enablement at Capella. And we'll talk a little bit about this data set. It was collected on the 4th, 23rd, and 24th of August 2019. There are about 204 image strips collected from an aerial platform, as Jake mentioned, and both north and south facing, with frequent revisits of the same area. So important point to make here is that for the same area on the ground, you might observe that area from the north, and then the next image might be from the south. That has an important repercussions that we'll talk about in the next slide. The details of it, it's an X-band. We collected quad polarization with a spatial resolution of about 0.5 meter. And our incident angle, our average incidence angle is about 35 degrees. Next slide, please. All right, so what's the value of SAR? Most importantly, that you can see through clouds, right? And since it has its own illumination, it's an active system, we can also image during day or night. It's a complement of optical imagery, and it can measure, you can think of it as the texture of objects. To the right, you could see that Jake built a false color image of the SAR data using the different polarizations. So in one of the challenges, it says lack of color. In this particular instance, we can do a pseudo color, and that gives us some of that information, some of that texture information that gives that shows us the different scattering mechanisms. So if you have a single scatterer or multiple bounds, etc. Also, you have one of the challenges of SAR is shadowing. You might have areas of occlusion where there's no data because something's blocking it. Additionally, layover. So I mentioned in the last slide that we took images from the north and from the south. Well, that will produce a different type of shadowing and a different type of layover in opposite directions, potentially. And that's one of the challenges of SAR as well. Understanding how the phenomenology works so that you can interpret the image correctly. With that, I'm going to turn it over to Todd to talk about the Maxar dataset.
Thanks, Jason. My name is Todd Bacastow from Maxar Technologies, and I serve as the co-chair of the SpaceNet Advisory Council. So it's a pleasure to talk a little bit further about the Maxar imagery today that was used in SpaceNet 6. This electro-optical image was collected on August 31st, 2019. It was from our Worldview 2 sensor. It was collected at a resolution of 0.5 meters or 50 centimeters at a off-nadir look angle of 17 degrees. So as part of this, as was mentioned earlier, we wanted to have these images be as close as possible to Capella's SAR imagery. And we provided 4 channels, so the RGB plus the near-infrared data. And you can see what this imagery looks like on the examples on your screen.
All right, thank you, Todd. So just in summary and kind of as a reminder here about how we split the training and testing data sets here. So on the left, we can see that we have our SAR collect and our optical imagery, and on the right, our SAR imagery only. The real purpose of this was to baseline how well SAR does, and also kind of look towards an application setting where we might see, where you might have a historical collective SAR and electro-optical data, but in a setting where you're really trying to map buildings, maybe the cloud cover is too severe, maybe your sensors are not really imaging at the exact same time, you might only have SAR data. So can you use that optical data in some way? Could you potentially perform domain adaptation, pre-train your models on optical data, and could that potentially then help you to work with your SAR imagery? And then another key component here is the annotations. So we used a pre-existing data set called the 3D bag data set, and this is updated monthly for the entire country of the Netherlands. So it's actually curated from the Netherlands Cadastry, Land Registry, and Mapping Agency. They have high quality building footprints of the whole country. Would highly recommend checking this out if you're interested in working in the Netherlands. So we cropped these areas down to the same area of our data set. And interestingly, these building footprints also have a paired LiDAR estimate of height. And although that could be used by our challenge participants, none of them ultimately chose to do so. However, it does enable us to start to investigate how these models perform based upon the height of different structures. And that's something we'll talk through in the results. Ultimately had 48,000 buildings included in the final data set split across our training and testing splits. Next, I'm going to turn this over to Daniel Hogan, who led creation of our algorithmic baseline, and he'll walk us through that as well as the metric for SpaceNet 6.
So as part of every SpaceNet challenge, we produce an algorithmic baseline, which is a working solution to the challenge statement. And the idea is to provide challenge participants with a starting point that they could elect to use in terms of either ideas or just code as they go off to develop their own solutions. So this slide shows some imagery of the algorithmic baseline in action. The first two tiles are examples of the optical and SAR imagery, as you've seen before. And so for training, since only the SAR is available, the third image there shows building footprints extracted by the baseline from only the SAR. And comparing that to the ground truth labels in the fourth image there, one can see a general correspondence, but also room for improvement. Next slide, please. The way the baseline works is that at its heart is a deep neural net, and specifically a UNet architecture with a VGG11 encoder. Now, this is a standard approach in computer vision, but for working with SAR, there are a couple of special developments that we incorporated. One is, as Jason mentioned, the effects of directionality and other geometric effects. So it was important for each tile to orient them as necessary so that the direction from which the imagery was recorded was the same in each case. And in the baseline, in order to benefit from this multimodal data set where we also had the optical data, a transfer learning approach was used, where first the baseline was trained on the optical data, and then it was trained in a second round on the SAR data to specialize on the type of data where evaluation was going to be done. Next slide. To evaluate model performance, we use an evaluation metric for building footprints that we call the SpaceNet metric. It's a very elegant solution to this problem. Basically, the way it works is that for each predicted building footprint, it is considered correct if it has an intersection over union with an actual ground truth building footprint in excess of 1/2, and it's considered incorrect otherwise. Then just compute the F1 score for those correct footprints. This is a good metric to use because it penalizes the right sorts of things. If a proposal just gets the location of the walls a little bit wrong, that's penalized lightly, if at all. On the other hand, if buildings are missed entirely or fabricated out of nothing, that's penalized heavily. And so this metric reflects a common sense conception of what it means to do well on a challenge like this. So using that metric, the baseline gets a score of 21 points or percent or 0.21. That number is meaningless in isolation, but to put it into context, if we skip the step of transfer learning with the optical imagery, that score falls to 14 points. And leaving out the optical pre-training and also the use of directionality, it actually slides a little bit more. Next slide, please.
All right, thank you, Dan. I'm going to be walking everybody through the challenge winners for SpaceNet 6, and we're excited to announce these today. These are our top 5. First place, we had Zbigniew Uwojna and the TensorFlight team. Second, we had Maximov KA. The third was the SatShip AI team. Fourth was Moda Kimura, and fifth was Selimsef. So the winning score ultimately ended up being a 42.4, which was about a 74% increase over the baseline. So we saw some significant growth here and improvement in performance, which is very exciting. The margin of victory here of 2.4 points, interestingly, was the second largest margin of victory across all of our challenges. The largest margin remains 5 points from XD. And that may be a record that's never broken because he was the first to actually introduce an ensemble of deep learning models to the challenge series. And that's a technique that all of our winners have used since then. Also, interestingly, here we can examine the precision and recall scores. You can see that precision actually drives the overall score a bit more. Precision, here we can see that about 1 out of every 2 predictions is a false positive. And the recall, you can see that it's about 1/3. So about 1/3 of the buildings are actually mapped, with 2/3 being missed here. So certainly some room for improvement. If we were to relax our IOU thresholds, these numbers climb up quite a bit. But this does highlight how difficult a challenge that this was. And if you would like to do a deep dive on some of our winner solutions, they're also going to be hosted on the same page as this video, and they'll walk you through what they did to really create these unique solutions and ultimately become a winner of the SpaceNet 6 challenge. So here are some of the winners' predictions for a larger area in one of the testing sets. And we can see here our building footprints in orange with the winner's predictions outlined in bright green. And you can see how challenging this certainly can be. Some of the challenges here are certainly some of the offsets of predictions versus building footprints, particularly in these northern areas. You can see how the building footprint predictions are slightly north of the buildings, and that's due to some of the off-nadir aspects of the collect. And that's something we will see in both optical imagery as well as in SAR data. So it's not unique to the SAR domain. This is simply a challenge from overhead observation and something that these algorithms have struggled to deal with. Algorithms certainly did better when the structures are much more rectangular or square in shape. More complex shapes are certainly much more challenging. So just a deep dive on what the winners ultimately did here, what architectures they used, how they ensembled them, the pre-training schemas, and training and inference times here. So we have our competitors on the left, our full top 5, as well as the baseline here. And we can see the different architectures that were employed. I think notably here was the emergence of EfficientNet. So if you're not aware, EfficientNet just recently set the benchmark for ImageNet recognition, and it did it in a way that had the fewest number of parameters to do so versus its other algorithms in this class. So it's much faster and it's much smaller, and that actually ends up translating to our training and inference times, which I'll talk about in a bit. Our winner ultimately ended up only using EfficientNet and ensembled 8 neural networks. The rest of the competitors used quite a few different ensembles. Notably, 4th place also only used EfficientNet, and only 2nd did not use EfficientNet. In terms of pre-training schema, only 2 of the top 5 ended up using the optical data in pre-training in any way, with the others finding that pre-training on ImageNet weights was just as effective, interestingly enough. It would be interesting to see if that would actually hold true as you move into other cities. Again, this is isolated just to Rotterdam, and I think further investigation really is required. Also believe that we think that further techniques such as domain adaptation or colorization in some way could be helpful, and that's something we're intending to test as a pre-processing step in the future. The training times here are also notable. Participants had actually up to a week to train their algorithms, and the longest training time here was just under 48 hours. So that's certainly interesting. Part of that is due to the size of the data set. It's slightly smaller than some of the other SpaceNet challenges, and as such, a training time is not really required. The models converge faster. Another interesting aspect here is the inference time. So our winner, Woj, was able to have actually the fastest inference time as well. So that just kind of speaks to the deployability. This is a very, very high speed versus some of our old competitions as well. So part of that is certainly due to the EfficientNet implementations here, which is exciting and really shows that these models could be moving towards deployable in the future, rather than just more of a conceptual AI approach that could work in the future. So getting into some of these results here, the influence of building size, basically what I'm going to do is walk everyone through some of the underlying attributes of the data set and how that ultimately affects overall performance here. So building size here, if we examine this plot on the right, we're interested in examining how recall changes based upon the size of our structures. And on our x-axis here, you can see our building footprint size in meters squared, ranging from 20 to 2,500 meters squared. On our our primary y-axis here, we have our recall scores, so measuring recall from 0 to 1, and then our number of ground truth buildings on red on our secondary y-axis. And that's actually this red line here. That's what you're seeing is the number of building footprints here. So the reason why recall is ultimately so low is we have so many tiny structures, which were generally impossible to detect. Our winners are first place is in blue, second in orange, and third in green. And as you can see, performance really starts to increase here. Around 30 to 40 meters, they're able to start detecting these small structures. And then it really peaks out around 600 meters squared. Also, interestingly enough, the winner's algorithm really outperforms the others in the 100 to 700 meters squared range. And that's really probably one of the main reasons why he won. He was able to detect more structures a little bit better than the other participants. So why does that happen? What is actually causing this challenge with identifying small buildings? So this is one of our tiles from our testing set, and we can see how challenging this really can be. I mean, even with optical data, I think detecting a lot of these buildings would be difficult. And again, here our ground truth buildings are in orange, and the predictions here are in bright green. And the only prediction here is actually in the lower left-hand corner, if you can see that. And so, one of the main ways that computer vision algorithms use and make decisions is through color. And you can see the color actually differs from the green suburban landscapes. Here's the trees in the background. That could be used for discrimination. However, with SAR data, you ultimately lack some of that color because what we're really measuring here is the types of backscatter, how things are bouncing off the ground, how the signal bounces off the ground and then returns back to our sensor. Furthermore, we also have a slightly off nadir perspective that 35-degree incident angle of the SAR collect, and ultimately that causes some occlusions as well. So we're starting to see some of these trees get in the way and really block out some of these tiny structures here, which really makes this a very, very challenging area. Another interesting aspect of this challenge was we had our LiDAR collects, as I mentioned previously, and they describe the height of each building. They at least estimate it. Obviously, these estimates are not going to be perfect. It's not true ground truth, but we can use it to estimate how recall or performance changes based upon building height. So again, very similar plot here. As with all of the plots, the number of buildings is going to be in red and highlighted here. And then also on our x-axis, we have building footprint height this time instead of area. Recall again on our primary y-axis here. And the winner scores are all colored the same, with first being in blue. So notably here that the short structures really are very difficult to detect in this challenge. Unsurprisingly, that seems to be a natural challenge. Number of buildings really peaks here around 10 meters, and coincidentally, performance actually peaks around 10 to 12 meters as well. And then it begins to gradually decline here, and that is really notable for the winning algorithm. There's certainly more noise for the second and third place algorithms. So why is that happening? Why do we see this gradual decline in recall based upon building height? So looking at these tiles, another tile here from our test set, we can see on the left, these are two of the tallest buildings in Rotterdam. So we have the building New Orleans here, and we have the building Montevideo, and they're around 150 meters tall. On the right, we can see our corresponding SAR image. So again, we have the same visualization, ground truth in orange, and then we have our predictions outlined in green. And we can see how the algorithms struggle also with this. And we believe that's probably related to this phenomenon called layover. So you can see these really tall buildings stretching out over the water. And what's happening here is the SAR sensor is actually positioned to the south. It's imaging and shooting a beam to the north. The beam will actually hit the top of the building first. rebound to the sensor, and then it will gradually go down and hit the bottom of the building as well, and then bounce back. And this causes the building to lean back towards your SAR sensor, causing this phenomenon and this noise. And I think dealing with layover is going to be, it was a real challenge for these SAR sensors or for our computer vision algorithms rather. And I think that's likely one of the complexities that we're seeing in the sense of not being able to map these buildings with our SAR data. So we also did a comparison versus optical data. So we retrained and tested the winner's algorithm on only optical data. So the participants didn't have this option. They had just the SAR data in our test set, whereas at SpaceNet we have both optical data in our training set, and we can test on the optical data. So what we do is we ultimately swap out the SAR data for our optical imagery here, and then we retrain and retest the winner's algorithms only on optical data. And the purpose of this is to baseline the performance on optical data to compare versus SAR, and we can also explore and compare versus our historical SpaceNet challenges, specifically SpaceNet 4, and I'll talk about that towards the end of the deck here. So comparing versus optical data, again, we wanted to look at the building footprint size. How does this differ? And also examine our overall scores. So you can see the overall score here. You can see that it dips quite a bit, dropping from a 0.42 down to, it drops from a 0.69 down to a 0.42. So the optical exceeding SAR data. And this really should not be surprising, right? We've seen that we know that computer vision algorithms are designed to work with optical data, and this is really why we built this data set and challenge. We want to see how computer vision algorithms can handle SAR data, and also incentivize research and development to start to improve SAR specific techniques to work in these settings. So examining this plot on the right again, we have our optical collect here in orange, and we have the SAR performance in blue. You can see that the optical certainly peaks faster. We're also able to detect some more small buildings. However, buildings at 20 meters squared are still generally impossible to detect even with the optical data. Furthermore, performance also seems to level off a bit faster, peaking around this 200 to 300 meters squared mark here. So our secondary performance, once again, examining building height. And again, we see our optical data in orange, the SAR model in blue. And we can see that optical peaks a little bit earlier here. You see this interesting peak around 2 to 3 meters, actually able to detect some of those structures. And we hypothesize that's likely due to color. We're actually able to use some of the colors to discriminate and pull out these tiny structures. And then we start to see the optical peak here around 0.8 recall. Certainly quite a bit of spiking here that we're seeing as well, which is interesting. This likely means that optical data is not, the performance of the optical model is not as strongly correlated with building height as it is versus the SAR. I think interestingly enough, for buildings over 80 meters in height, we can see that there's a bit of a divergence there as well. So we also wanted to do a comparison versus SpaceNet 4. And Adam talked about this a bit, but the SpaceNet 4 data set is unique in the sense that it isolates look angle as the independent variable that we can examine. So we have Atlanta with the WorldView 2 sensor passing overhead. It collected 27 different images from 27 different look angles in a span of 5 minutes. And as I said, that really enables us to isolate look angle and evaluate how that changes and affects our model's performance when trying to map these structures. It's a good comparison as well because it's the same sensor versus the Rotterdam Collect WorldView 2. And just looking at this figure, you can see this is our satellite path collecting from both north and south facing look angles. Each one of these dots is where it collected an image for SpaceNet 4. Also mentioned that this data set is just like SpaceNet 6, also hosted on our S3 bucket. So if this is of interest to you, we welcome you to download it and explore. So comparing directly with SpaceNet 4, we have our looking at this graph here, or this table, we have our cities. So Rotterdam versus Atlanta, SpaceNet 6 versus SpaceNet 4. We have our modalities. Obviously, we only have optical data with Atlanta. And we also have our off-nadir look angle here. So how the ground is being observed and from what look angle it's being observed from. We also have our competitors, so our winner Woj and also Kanab, who won SpaceNet 4. So you can see the overall score here, looking really at this 17 degrees off-nadir look angle first. For the two optical collects, you can see that Woj's performance is actually slightly lower versus Kanab's performance at 17 degrees. And there's likely a couple reasons for this. First of all, these are two obviously different geographic areas. That's certainly a component. Another aspect of this is that the Atlanta data set is about 3 to 4 times larger than the Rotterdam data set. So that can aid and boost performance. Another aspect here is that Kanab was able to train his model on all 27 look angles versus we only had the single look angle for Woj's model. The final aspect here is that Woj's model is optimized for SAR data. You could probably do some more advanced pre-processing to really improve these scores and make it more of an optical centric model, as we really didn't do anything to modify this model other than swap out the SAR data for the optical to calculate these scores. Furthermore, you can see how look angle really starts to affect our performance differences here. So as we go from 17 to 35, performance drops by about 5 points for Kanab. It drops off here as well, but this is really due to the SAR domain. We can hypothesize a bit though. So perhaps if the SAR data was collected from slightly more on nadir look angles, what we would see is a general improvement in these overall scores here. Potentially, you could see a small performance boost in SAR data. So that's something to consider. Obviously, SAR does need to be collected from something slightly off nadir. That's how it works. However, maybe that slight change could be helpful for performance. Regardless, so just in summary of the results, we're really excited about these results. I think it highlights, this was a very challenging competition. It shows that there's room for growth. But as you look back to our challenges starting at SpaceNet 1, the winning score there was around a 0.25. So SAR data has already exceeded that mark. And I think with further research and development, the ability to use SAR and to conduct some of these applications, specifically foundational mapping, seems very achievable, and we hope to continue to incentivize and grow that with releasing more high quality data. So with that, we have a few announcements. I'm going to turn it back over to Daniel Hogan to talk about some of the things we'll be releasing in the future.
Our first announcement is that in early July, we will be releasing a new pre-processing library for preparing geospatial data sets for deep learning. This library will be built into an upcoming release of Solaris, and it will include a suite of tools for working with SAR imagery. With the library, users will be able to construct data processing workflows out of pre-made and custom building blocks to quickly prepare data sets for advanced applications like deep learning with multimodal imagery. Next slide. The next announcement is that we will be releasing an expanded version of the SpaceNet 6 dataset. This new data release will cover the same geographic area based on the same original SAR collect as the SpaceNet 6 training data, but it will include new and expanded synthetic aperture radar products, in particular complex SAR data, that is to say data with phase information. This will extend the value of SpaceNet's SAR dataset for research and development. And the next announcement is from Ryan.
Thank you, Daniel. We're also excited to announce that the SpaceNet community will be offering, for the first time, a self-service labeling capability. Since the founding of SpaceNet back in 2016, when it was just In-Q-Tel, CosmiQ and Digital Globe, our focus has been enabling an open source ecosystem consisting of robust data and code. We view this self-service labeling interface as the next step of that. And so throughout the remainder of 2020, you'll be able to create your own labeled data from the entire SpaceNet dataset via a web interface. We'll be doing this in concert with Xavia's GroundWork product. So stay tuned for additional announcements on that release. Next, I'd like to turn it over to Adam, who will give insights into what we have planned coming up for SpaceNet 7. Adam, over to you.
Just as SpaceNet 6 was really exciting for the team, given the multimodal nature of the challenge, SpaceNet 7 is something that we're very excited about because this will be our first real foray into temporal analysis. So SpaceNet 7 will be labeled the Multi-Temporal Urban Development Challenge, and it will feature a deep time stack of planet imagery covering dozens of locations. And you'll see on the right here a GIF over time development in a certain region where you're building up both roads and buildings. And so the goal here for SpaceNet 7 will be to track urban development at the building footprint level over time and track both the building footprint and then as well as the ID for that. So there's some nuance there, but we think that will be very impactful. That will launch in autumn of 2020. And also very exciting is that it has been accepted as a NeurIPS competition. So this is a very prestigious conference, obviously, and we will announce those results in December. Next slide. I'll hand it back to Jake for this one.
All right, thanks, Adam. Yeah, so we've presented quite a bit of information today, and I want to say that we're super excited about the participation in SpaceNet 6 and also the winners that we saw. I mean, we really had some world-class computer vision and data scientists participate in SpaceNet 6, and we're thankful for them for their solutions and contributions to this, as it's very important to us and to the community to continue to advance these things. If you're interested in learning more about SpaceNet, and particularly downloading some of these winning solutions, you can check out our GitHub repos. So we have Solaris, which is our pre-processing and deep learning library geared specifically towards geospatial data. You can find that in our GitHub page. And also the SpaceNet repo will contain all of our winning algorithms there. Our website you can find at spacenet.ai, and you're actually on that website right now, so feel free to click around. Our open data is all hosted via the AWS Open Data Program, so you can explore the different cities and figure out how to download those for yourselves at the arrow on the top right there. Our blog, we have a very active blog, so we do a deep dive on all the results, similar to what we discussed through today, as well as a number of other interesting projects that CosmiQ helps to lead and develop. We have a podcast called Training_Data, and that's available through all of our different podcast mediums that you can find it on. And ultimately, we are very active on Twitter. So we have a couple different handles there: SpaceNet_AI, at CosmicWorks, Maxar, Intel AI, AWS Cloud, as well as Capella Space, Planet, and all of our other partners. So thank you again for your attention, and we will end the slideshow there.